Thanks, Josh, for your presentation. Really cool that one of your lessons is like visualize stuff because we're presenting about visualization here. So yeah, visualization is actually useful. A lot of people do just render data. There's a lot more to it. Like I like to think about visualization engineers as people who are specialized into information design and computer graphics as well. So try to find meaning in data. So for most of the things, we're customers of all of the stuff that you guys do. So from a customer perspective, that might be interesting as well. So I joined Uber about 2 years ago. I have a background slide, but this talk is going to be specifically about an open source framework that we somewhat recently open sourced. It's called Deck.gl. And as you can probably imagine, like there's a lot of geospatial data at Uber. Like we process billions of GPS points every day. And so that's one of our biggest assets. And we ask ourselves the same question. It's a very similar question on like, hey, should we rely on a third party or build our own stuff? But more around frameworks, right? And so we've seen many limitations around visualization and visualizing like multiple elements in real time on a screen. So we started kind of like crafting our own solution to it. So it does a very specialized and specific thing, I feel, pretty well. And then it relies on other libraries for the rest. So anyway, quick background. This is my link to France. Like I worked 3 years in Paris at this company called Exalid. Does anyone know this company? Oh, that's awesome. Yeah, I was kind of scared that nobody would raise their hand. So it's a French search engine. And then after that, I moved to the US in about 2010 to work for this company called Sencha. They build UI frameworks, one of them called EXTJS. And then after that, that's when I started kind of like connecting with big data, quote unquote. I joined Twitter in 2012. And so instead of only focusing on building frameworks around UI and visualization and computer graphics, I also started kind of like focusing more around the type of data that we're getting and how to get insights from that information and how to actually process the data in meaningful ways. So I spent there 3 years. I was leading this project called interactive.twitter.com. You can go there. Right now it has a bunch of public-facing visualizations that we used to do for like media and communications, like, hey, how the Oscars were lived in Twitter, like how many tweets were they for each movie or stuff like that. So we would run really quick queries. We would work with this person called a data editor, and we would build a visualization that people could kind of enjoy on like how different moments were lived through the Twitter platform. So after a few years of doing this, this was like really fun work, and I feel in a way it was very selfish because looking back at it, like I'm not exactly sure what the impact was of the stuff that I was building and we were building. Like it really was fun and engaging, and we would get millions of views in some of the products, so that's definitely good, like PR. But I had this kind of feeling in me that like I thought that visualization could really have a lot more impact than just like storytelling and PR. And so that was timed perfectly with like a recruiter from Uber sending me a message, and Uber gave me the opportunity to basically execute on a vision of forming a visualization team around a lot of different internal tools and try to provide impact around data exploration and just getting insights from data. So at Uber, I started with what was, how do you build a visualization team in a company? It's kind of hard. Like there aren't that many visualization teams. You may hire front-end or visualization engineers, but they're not all connected into like one cohesive team. And so in order to get buy-in from other folks and building this group, we started with what was the most like clear and actionable and kind of easy to explain way of like how we can provide value from your data and through visualization. And so that was, of course, like all of the business insights stuff, right? Like, so we started mapping a lot of the key metrics like trips and gross bookings and all of the financial metrics into like, expository visualizations where people could actually see how the business was like moving. And then we built some exploratory tools around that where you could quickly with drag and drop like create some queries and get some insights from that. very tied to reporting and to like data presentation. Those tools were internal tools. They ended up being used by 98% of the company on a weekly basis, so huge adoption internally. One of those has hundreds of thousands of queries being run weekly, like manual queries, which is kind of crazy. And so that gave us enough traction to start like betting on more like specialized things. So we started this other team called the Advanced Analytics team. The focus for this group was mostly around data science and data products that serve or are powered by data scientists. So things that fall into this group could be A/B testing, like experimentation, all of the visualization around that. Machine learning platforms. So we're building our own homegrown like machine learning platform where you can define, train, and deploy models at scale. Like machine learning is used at Uber in a lot of different things, including like ETA calculations for all of your trips, extracting features from satellite imagery and stuff like that. What else in advanced analytics? Geospatial stuff. So a lot of geospatial stuff falls into the advanced analytics group as well. So that went really well as well. And then we started a third team, which I called core visualization. And it has two functions. One of it is mostly powered by computer graphics engineers. One mission for it is to build computer graphics frameworks that other engineers can use to visualize large-scale, kind of create data-dense visualizations. And then the other mission for the team was a partnership with the Advanced Technology Group, which works around the autonomous vehicle stuff, to visualize, to create like 3D environments on like what a car perceives and predicts and how it plans its next moves. And all of that, like we used Deck.gl for all of that for 2 years, and then one day we said, well, we should probably open source it. The common themes then around the group, this is like spread around these three teams, but there are these themes, a lot of dashboarding, like abstract data visualization, a lot of mapping, of course, given the nature of the data set that we handle, and then the only way we have to scale as a team is just to encapsulate this knowledge into libraries that other people can use, right? Cool. So today I'm going to talk about one of those libraries. It's called Deck.gl. It started as an internship project from one employee who's now full-time. Now it powers like half of the or more of the geospatial products at Uber. So it's like a pretty fundamental tool that we use here. What it is large-scale WebGL powered data visualization. When I say large-scale, it doesn't mean that you need to visualize 1 million points, but you can, or millions. But you can process them as well. And so there's always this kind of like question on like, okay, how much you should be running on the back end? How much can you run on the browser? And as you've probably seen through the years, like the web has evolved a little bit from doing everything on the back end to like dropping a little bit more functionality over to the front end. And so there's always that question specifically with visualization of what to do. And so we're asking that question all the time, and we're trying to find different ways of doing this on the client. So I don't have internet, but you can go to Deck.gl and you'll see a bunch of demos. This is the website. There's a gallery on the top left with a lot of examples of different layers. And the structure for this talk is going to be, I'll show you a bunch of the principles behind the library. We'll go through how it's being used at Uber on what I can show. And then some of the architecture for the library, and then we'll go through a specific, more advanced example. So on the principles, one of them was high-performance GPU computing. So WebGL is an API that lets you access the GPU in the browser, and it is conformant with the OpenGL 2.0, I think, API. WebGL 2 was just out. So there's like this new set of capabilities that you can do around GPU, like data transformation using GPUs on the client. So we decided to go with that solution in terms of like visualizing data. And then we have layers on top of it, right? So in this case, you're looking at dots, a scatter plot layer, and that's on top of a base map. The base map is using Mapbox, so we play really well with the Mapbox library, which, by the way, there's a WebGL version of it called Mapbox.gl that has this perspective mode, right? So we have all those camera synchronizations between our library and Mapbox so that they play really, really smoothly. And then it plays really well with React as well. So as you're building your React application, you can just import Deck.gl and it follows the same patterns. It follows this kind of idea around instancing and layering. So the instancing idea, if you've ever played with D3, or just like in general visualization, the idea of instancing is you have an array of elements, right, that you want to visualize. And what you'll do is you'll instance the same shape multiple times, and then you'll make some tweaks to the attributes of that shape so as to modify them. So that can be seen pretty clearly in these examples, right? On the top left one, you have a scatter plot layer. Actually, we're not tweaking anything on that one. We're just, tweaking the position of the points, but we're instancing multiple circles, right? The same would happen with the hexagon layer. Like we're instancing multiple hexagons, one for each element in the array, and then we're tweaking the color of those hexagons. So that's kind of like a pretty fundamental notion around information visualization is the fact that that data binding notion. So coincidentally, it also happens that like WebGL is extremely good at instancing. You can have primitives that you can quickly copy, and with one single kind of GPU call, with one single API call, you can kind of instance all these elements. So we kind of use that trick and connected it with that notion. And then the layering paradigm is, it's a pretty well-established paradigm in mapping, right? You have layers, you have, land and water, labels, road segments, et cetera, et cetera. So you have a lot of different layers that you can turn on and off in your map. What we provide is a set of layers where you can visualize your data on top of that. Some of these layers don't only like render data, but they do a little bit more. They can aggregate the information, they can filter the information, they can provide different sets of interaction. So, for example, in this specific page, I think we're visualizing personal injury road accidents. Not the best and happiest data set to visualize, but it was an open data set. So. We're changing the granularity level at which we're like aggregating this data by hexagon, right? And then after that, we are changing some of the visual attributes for the hexagons. And then finally, we're filtering by top percentile. So we're removing out of the distribution the top percentile of that distribution to see the underlying distribution on the map. So these things can be done, again, with WebGL2 on like kind of this thing called transform feedback, which I'll talk more about later. But you can do like just general GPU kind of data processing in the browser. And so again, the question asked is, okay, how much should I just like offload to the browser versus doing it myself, and have that sort of like responsiveness that we're seeing here in this video. A lot of the needs within the advanced analytics team were outside of geospatial, and actually during that internship project, like Deck.gl was never meant to actually be a full geospatial library, but we ended up tuning it for this just because we are dealing with so much map data. Who knows what this is? Clustering? Yeah, so it's like this Disney algorithm where you do like you reduce the dimensions of the objects and they get clustered into different places, and so you could imagine like every sphere here being, I don't know, a driver, for example, and then we're passing in some multidimensional data about these drivers, and we're finding clusters of information there. And so I don't know if this cluster would mean anything. It could be like, okay, all of those are like fraudulent trips, and so we just suddenly found like a cluster of fraudulent drivers. So machine learning is used for fraud detection as well, quite a bit, and very successfully. actually. And so what this does is not only displays that cluster, but it's called an embedding, but it also shows you the process of this clustering. So it's a live process. It's not like you get the end result, but you actually have the full set of computations happening in the browser as well. And then finally, something that we did was we took a completely different approach to something, and I'm not sure if it was a good idea. I feel it was a great breakthrough still. I haven't found any shortcomings for it, but one of the problems of like dealing with GPU programming, GLSL, is that you only get certain precision for floats. So instead of getting like 64-bit precision, you get only 32-bit. And that's actually pretty annoying, specifically when you're doing mapping stuff, because you may go from like a very zoomed out level of the whole world to an intersection level, and you want to see changes at the centimeter level of what's happening, right? And that's more than 32-bit. And so all of these maps engines like do a lot of crazy stuff on the browser, like spawning multiple web workers, doing CPU computations, changing coordinate systems, doing all these things to try to kind of work around this issue. We went completely a different way, and we decided to like emulate all float 64 computations in the GPU itself. So by passing in two 32-bit floats as a vector of two components in the shader, you can emulate all math functions. So we redefine all math functions again, so that we can have 64-bit precision on those. So the difference is this one. I can show you this really trippy image, and then on the left, you'll see it stop at a certain zoom level there, and then you'll see how much more you get with the 64-bit precision. Yeah. Of course, this comes with a trade-off in performance, right? Instead of using the built-in math functions, we are using some sort of custom math functions that pack and unpack these two floats. But still very useful, and I'll show some examples of like why and how we had to do this and why it is useful. Cool, Deck.gl at Uber. We use it a lot in the internal tools, and unfortunately I don't get to show you much of that, nor the data, but we were able to manage to do something with some fake data. And so these are some of the examples. We use it a lot for visual exploratory data analysis. So the main idea behind it being, is this playing or not? Oh. The main idea of it being that like you can pass in a bunch of data to a map and then do a lot of like computations and aggregation and things like that in the browser directly. So getting the insights really like in real time and not really having to wait to call for yet another query when you need something that's like a simple aggregation or filtering. Oh, there we go. So in this example, for example, where I'm showing everything in one really concise video, but the main idea is you can find different levels of aggregation for your data. You can show it in different ways as point data or aggregated information. You can find links between pickups and drop-offs. You can do filtering and brushing within your data, and all that stuff happens in real time. Cool. So now you've seen some of the use cases, principles and use cases of the framework. How does it work? So I would say that there are like 4 main boxes here. It all starts with the data on the top left side. So you have a bunch of data, you want to visualize it. You may need a map or not. If you need a map, this matters. This is React Map.gl, another library that we built that provides a thin interface that makes it React friendly to use Mapbox. And why did we do this? Because React is pretty popular, and React Map.gl is one of our most popular libraries, open sourced. But also because we can control the map state and the viewport, and so we can connect these two libraries together so that they play really smoothly in terms of like perspective mode and stuff like that. So you pass in the data, you have a layer manager. And the layer manager may contain multiple layers, like I showed you in the previous example, where you can turn them on and off. You can change the order of the layers, how they're being rendered, and stuff like that. And so in this case, a layer can have sub-layers. We'll talk about it later. For example, you could have a GeoJSON layer that renders points with a scatterplot layer, lines with a line layer, and polygons with a polygon layer. And so it's just like managing other layers. But you can simplify this as only one layer. Imagine this is a scatterplot. You want to just render points. This will create a bunch of circles, and the circles will get rendered. And everything here happens under the hood if you want it to happen under the hood. If you want to plug in and write in your own GLSL code, you can do that too, but you don't have to. That's the good part. Okay, so a little bit more about this ecosystem. By the way, anybody has a question on this? Is it clear enough? Yes?
Where does the data come from? Is it a file or can it be a database?
Where does the data come from? It can be anything. So the tool that I was showing, you can just drop in a CSV file, but the data is an array of elements, whatever you want it to be.
Do you have connectors to different kind of databases?
We don't have connectors to any kind of databases. It can be, it's just accepting some JavaScript model. So we don't do any backend work. But we love to partner with backend people because we need the data. Yes?
When you say you're working on large data too. Thank you. When you say you're working on large data, I mean, how large can it be? It's a CSV file. You cannot get like more than what the file system can.
Yeah, definitely.
How do you do
that's
it?
That's definitely a good question. So for sure, this is not like the MapReduce type of like large data or GPU database. Like this is not 500 million or 1,000 million like elements, but you can go to the millions. So it could be 2 million elements. You don't have to receive them through CSV. You could pass in a bunch of binary data if you wanted to.
Okay, thank you.
Yep. Cool. So React MapGL, the friendly wrapper for Mapbox.gl data. So what you do here is the wrapper is very minimal. You can just call mapgl. This is JSX code. And inside of it, you can pass in layers. Layers can be anything. It can be a canvas object, an SVG object, whatever overlay you'd like to pass in. This is where Deck.gl plays in. You can pass in a Deck.gl instance. And what Deck.gl will do is it will manage WebGL canvas and all these layers, ordering, z-fighting, all these different things that you need to take care of with WebGL, like all of the resources and the performance stuff for you. LumaGL, as I mentioned before, can happen under the hood. And this is, again, something kind of similar to what Josh said. Like when you move over to a third party, like you have this issue where like suddenly developers cannot go there and tweak it. So we've evaluated other libraries before deciding to go with our own, mainly because of two things. One of them is that the priorities sometimes diverge. So some libraries, for example, right now are way more excited with implementing VR features, web VR features, and implementing like WebGL 2 features. And we care more about WebGL 2 features because we care about GPU programming. We don't care that much about immersive environments right now, at least. So that's one of the reasons. The second one is support. So there's a lot of open source libraries, and they seem great, but there isn't like a good model for getting support from them. And so, there's zero reliability. Tomorrow, like somebody may say, well, I'll just dump this library and I'll go and build something else. And you're like left there without full knowledge of the code base and now have to maintain that. So given that sort of like low level of reliability, we decided to come up with our own set of libraries. This one was built from scratch with an ES6 code base. So we're using main classes to wrap in main WebGL 1 and 2 entities. And then it's WebGL 2 ready, so it has a lot of the goodies of dealing with data transformations in the browser. There are three ways in which you may want to develop with Deck.gl. So now you downloaded Deck.gl. Okay, what should I do? The quickest one is using some of the existing layers. There's like a dozen different sets of layers that you can use to process data and visualize it. This is an actual screenshot of some of the layers. Another one could be creating an adapter layer. So you want to get some data in some format, do some processing with it, and then render it using an existing layer. This is a very common type of set. For example, S2 cells. Anyone is familiar with S2 cells? Okay, Google has this kind of partitioning of the world into cells. They're called S2 cells. They're just like parallelograms, like they're just polygons, right? So you could have a layer that gets in a bunch of IDs of S2 cells and then uses the polygon layer to render like parallelograms, basically. So that would be an adapter layer. And then finally, you may want to extend the layer, like add new functionality to an existing layer. Like the brushing stuff that I showed before, where you filter stuff as you move your mouse. That could be a new feature in an existing layer. Cool, so how do you use existing layers? You go to one of our examples. We have a pretty large set of examples. Each one of them is featuring a core layer. There's a view code link here. Pretty straightforward. It tells you how it's being executed, so you get to see some of the instancing of that class there. If you're interested in knowing more about the props, the properties that you're passing in, there's interactive documentation where you can just play out with all of the props and read a little bit more about how to use that. Everybody knows that when they open source libraries, like documentation is like 80% of the actual work. Like people hate documenting stuff, but when you tell them it's going to be open sourced and everybody will be looking at it, like it's a great forcing function for that. So we have really well documented code. I'm really proud of that. And so as you can see in this code, the scatterplot layer is passed in as in a component that renders a Deck.gl instance, and then as the layers passes in the scatterplot layer. Sorry for the ones that cannot see there. And so finally, we use React Map.gl. So this is the Map.gl component. And what are we passing in as overlay? Well, we're passing a Deck.gl overlay, which is the component I showed you before. So it's like 3 steps, and you get something out pretty quickly. The second one is extending layers. So you could have an arc layer, and then you want to add some brushing functionality to it so you can extend it. How are we doing on time? 15? Okay. So you can use custom shaders for this. That's one example of something that you would like to extend. So for example, you may want to have a rounded rectangle layer. I would definitely not recommend for visualization rounded rectangles, but it's a good example because it extends the scatterplot layer, and then you change the primitive to be a little bit different. You pass in a new prop, which is a corner radius, when you draw the layer, and so you override the draw, basically call the super for that one, and then pass in a new prop. And then on the shaders piece, we're reusing the vertex shader, but we're passing a new custom fragment shader that we decided to code ourselves. And what this fragment shader will do, fragment shader handles with like the pixels that get drawn on the screen. By pixel gets called once. You can imagine a callback that gets called every pixel on the screen. So it'll decide whether to discard that pixel or to render it based on the corner radius. Hopefully that was clear. So this is how it looks like. So we're basically creating a circle here that we're like a little bit skewing based on the corner radius, and then we're deciding to either render the pixel with a color or discarding that pixel. And that we're doing that for every pixel. Cool, and then finally composite layers. As I mentioned before, you may want to have a composite layer when you're like managing multiple primitives into one layer. You have like a GeoJSON layer that has points, polygons, lines. You're doing some data processing and aggregation on a layer, so you may want to break it down into multiple pieces. You want to be able to have something that's testable, reusable, and so on. Cool. So those were the examples. Just like Josh, when I joined Uber, I stopped coding, and then I went back to coding a year and a half later, and I remember why I stopped coding in the beginning. I decided to build this custom example that uses some wind data and to build some custom layers for it. So the challenge was using some vector field information and then to render that as different layers in terms of vector fields. But there's also a pretty interesting data processing element to it that I'll get to, and it has some interesting math. So this is a remix from another example that a creative developer that now is at Facebook, his name is Patricio, he used this data set that I collected in the beginning to build a remix of that visualization, and now I'm remixing his remix. So, so the data set looks like this. You have multiple wind stations in the US, and every wind station, every hour, kind of collects data around wind direction, wind speed, and temperature. So here we're encoding direction with the angle, speed with the radius, and hue or color with temperature. Now, something that really bothered me about this data set was that it wasn't fully uniformly interpolated in the US. Like, if I pick this point here, like, I would need to do some sort of average to figure this out, right? Like, I couldn't just have a really regular grid that will tell me some sort of approximation of the wind here. But one of the cool things that you can do with WebGL, which is more data processing. So WebGL is really good with triangles. You can render triangles really fast. And if you're rendering 3 points and each one of them have a different color, the GPU itself would just handle to do all the linear interpolation for the colors for you for free, which is amazing. So what we did was we encoded every value of every point into a color. So wind speed into red, wind direction into green, temperature into blue. And we basically plotted the dots and rendered them into an image, a texture, right? And what the GPU did for us was just like interpolate all the wind for free. So that was pretty awesome. This is how it looks like. So we did a Delaunay triangulation, which is when you form triangles out of random points, and then we rendered those triangles and got the colors interpolated for free. The next step, so now we had the data. The data is an image. No matter where you pick the point in that image, we have an interpolated value for that wind and direction and temperature and so on. So the next step was to create a layer to visualize this vector field. Again, this instancing paradigm where you have lines and you can multiple times kind of clone them and instance them. So we created that one. This is another example showing some of the stations and the wind. This is another one adding some shading. So this is the Delaunay triangulation. I just created a layer on top of that so that we could visualize it and playing with some lighting. This is how the first iteration looked like. So we are switching time every one of the 72 hours for wind. And then you have that point here, which is the windiest point in the US. It's called Mount Washington. It's a mountain, and it's super windy. But it's pretty cool to be able to really quickly spot that outlier from the data set. And then you have 3 layers here, right? You have the elevation layer, which is this approximation of elevation. You have the vector field layer, and then you have the sites layer, which is every dot is the wind station. So you get to see how they're interpolated. The next step for it was to create these particle effects. And particle effects are kind of hyped, and it's easy to create them in WebGL too. So it's like a demo that you'll see multiple times. And I won't go into the rendering pipeline kind of into details, but something that's interesting is the vertex shader piece. So when you're passing in a bunch of points to the GPU, it goes through this process called a vertex shader, and that's programmable, meaning you can type in some C-like code, which is GLSL, and you can change the position, translate, rotate those points in the GPU and parallelizable. And before that, in WebGL 1, you couldn't get the result back. It would go the entire pipeline until it would get rendered into the screen. But somebody thought that it would be a really interesting idea to actually go through the vertex shader, do some math around those points, and then get those points back as a buffer. And you could imagine that being used with particle physics, right? Like you can get the current position of the points, you apply some wind direction and speed, and then you get a new particle of points, and you do this process, you iterate with this process until you get the particles moving. So although this is not the actual, I think it's loading, let's see. Although this is not the actual data, because of like all of the interpolation that we had to do during the Delaunay triangulation, it kind of shows an approximation of what it could be. Let me see if it'll play. There we go. So it shows some vortices around Florida. And what we do here is we drop like millions of particles and we let them just see where they go. And every particle has a time to leave. So after like a few seconds, we just like remove it and then drop it into some other random location again. And then, if you change the wind, like all the particles will adapt to it. So of course, this is not used at Uber because we don't have this data. But I had to build an example without Uber data. So one of the cool things is that now we're thinking about creating some of these layers into some core layers so that you can use them with some of the vector field data. And don't think about this being only for mapping. We're just using a map, but it could be for anything. Cool. So this is the part of the team that worked on Deck.gl for the last 2 years. And I'm just taking all the credit for it. So thank you.